With so many turbocharged cars around, it's about time we checked how much we really know about the intricacies of these systems. So, what does a turbo actually do? This very simplified graphic shows a forced induction system in its most basic form. The air enters via the air filter, passes through the compressor wheel of the turbo, where it's pressurised, to the plenum and past the throttle body, and mixes with fuel to be burnt in the engine. It then exits through the exhaust manifold into the rear of the turbocharger, where it drives the turbine wheel and exits out the exhaust pipe. The increased speed of the turbine wheel increases the speed of the compressor wheel, thereby forcing more air into the engine, increasing its available performance. We asked Brett Lloyd from GCG Turbochargers to explain what makes an efficient turbocharger.
The most efficient turbocharger available on the market today are the ball bearing turbochargers. They come in a variety of sizes from 320 horsepower through to 800 horsepower applications. In today's performance market, there are two styles of turbocharger. There's your plain bush bearing turbo, which has been around for 30 odd years, and now we have the new generation GT series ball bearing turbochargers, which actually run a ball bearing cartridge assembly.
The turbocharger is made up of three major components. The first is the compressor cover, the starting point for the intake air. Next is the centre rotating assembly or cartridge assembly. This contains the compressor wheel, the diffuser plate, centre housing and the turbine wheel at the back. Last is the turbine housing or exhaust housing, which is bolted to the exhaust manifold of the engine.
The turbine end determines how soon the turbo will respond, and the compressor end determines how much CFM the turbocharger will flow, and then that determines how much horsepower the engine can produce.
First of all, let's pull apart the centre rotating assembly.
Here we have the compressor wheel. These come in a variety of sizes. A typical upgrade for any of the Nissan applications, being SR20 or VG30, 300ZX, whereby we actually machine out the compressor housing to suit a larger compressor wheel. What that allows is the customer to run a little bit more boost and get more airflow out of his turbocharger. Secondly, we have the turbine wheel.
The turbine wheel also comes in many different sizes. Here's a few Garrett turbine wheels: the T2, the T3 and the T4.
Okay, we can remanufacture or reuse turbine wheels, and as you see here we have a variety of wheels ready for regrinding. When the turbine shaft wears in the bearing journal area, as you can see by the grooving in this particular wheel, we take the wheel, set it up on the grinding machine here, and typically take 5 or 10 thou off it and put oversized bearings. That allows us to reuse one of the most expensive parts of the turbocharger and keep the cost of repair to a minimum.
When you refer to a ceramic turbo, such as the standard ball bearing turbo in the Skyline GTS-T and other cars, you're talking about a ceramic turbine wheel only. These can be readily improved by modifying the housing to accept a larger steel turbine wheel and a larger compressor wheel. You can see here how much larger the replacement is. This assembly just bolts back on, resulting in major gains in turbine flow and a 15 to 20% performance improvement without increasing boost. Drivability remains similar to the standard unit.
As you can see with the factory turbine wheel, it is ceramic. You can't run over 14 pound of boost with it because it will actually throw off turbine blades, as you can see here. That is a limiting factor of the stock turbocharger. When we go to the steel turbine wheel, the amount of boost you run is unlimited.
Unlike the turbine wheels, compressor wheels are never ceramic. They're always an alloy base. Although some Japanese manufacturers are starting to play with titanium. So do all turbochargers rotate in the same direction?
The standard is to have a clockwise rotation. You'll see that in the angle of the blade and the way it rolls over, both on the turbine wheel and the compressor wheel. The variance to this that we have found in the market today is the current Lancer Evo 6 and Evo 7s, which run anti-clockwise rotational turbos. With those turbochargers, we can't find any upgrades. Manufacturers obviously don't want us playing around with their product.
So when it comes to turbos, is a bigger one better?
If you've got a too large a turbo, you'll find that you've got excessive turbo lag. And what that is that it takes a lot longer for the turbocharger to come on to boost and give you that kick in the pants drivability. So you'll find that instead of coming on at 2.5 to 3,000 RPM in a 4-cylinder application, it'll come on 4,000 plus RPM. That's turbo lag. That's too big a turbocharger for your needs. If you've got too smaller turbocharger, what you'll find is that it'll be really responsive really early, and then in the higher RPM the turbocharger will just die off. It'll get to its peak output and drop right off in performance. So the ideal setup is something that responds early enough but holds full boost all the way through the RPM running.
One characteristic of turbo systems is that they generate a lot of heat. But by installing an intercooler between the compressor wheel and the throttle body, the air can be cooled and made more dense before reaching the engine, resulting in a more efficient and more reliable system. We asked Mick from Mick's Metalcraft to explain how this occurs.
The main advantage of intercooling is colder the air going into the throttle body from the hot air from out of the turbo gives it a performance advantage. And if you drive a turboed car on, say, a cold night, it's a lot more responsive than it is on driving on a really hot day, you know. So obviously the air is getting cooled through the intercooler, so giving it that more performance, and also then you can upgrade the boost.
So should you buy a custom-made intercooler or pick up a cheaper second-hand Japanese import?
They are cheaper, and to say if you don't have an intercooler on your car, yes, it will be a little bit better. But if you're after the utmost performance, usually the cost of buying the cheaper intercooler and then piping it up is usually a waste of money, because you don't gain that much out of it for what it's going to cost you. Custom intercoolers, you'll get it to fit your car perfectly to get the utmost efficiency out of it.
So what about cutting down a truck intercooler?
Using a truck core and then cutting it down, you think, well, I've got this big truck core, I can cut it down and make 3 intercoolers out of it, so you know it's going to be more beneficial. But the truck cores don't usually flow. Its rev range is usually like 4,500 to 5,000 revs, and us guys on the street like to take it to 7 to 10, so they just don't have the flow characteristics there, you know.
Can top mount intercoolers be as good as a front mount?
Top mount intercoolers on a factory car are good for what they're made for, is a production car. But for performance advantage, obviously it's better than having no intercooler. But although you've got a scoop on the top and it's scooping all that cold air in, there's also all the hot air rising through the engine, which is sort of like fighting each other, so they're not that as efficient. And where guys have a WRX and they take their top mount intercooler off and then they go buy an aftermarket top mount, okay, it will cool that little bit better than the factory one, but still you've got the hot air rising, so for the expense of doing that, it's not usually much more expense and you get the front mount. There's different designs of intercooler cores. There's 2 here. This one here is a bar and plate construction. Bar and plate being it's got square edges and it's all locked together. I do believe these are cheaper and they do work very efficiently because of the tube being round, so when the air hits it, it actually goes through the core, so it cools better. Whereas this one here, with its got its flat surface, there's obviously a small percentage of air that hits it that will repel away. And for when they are this big, sometimes if they're really large, they have trouble getting air through to the radiator, causing the cars to overheat. If you look at both cores inside, they've both got this mesh design here for cooling. So they're both pretty much the same on that par. So if you were going dollar for dollar, the money you want to spend, this has to be a bath. You get more for your money.
End tank design is also vital. Imported tanks like this one are cast aluminium rather than rolled sheet metal.
But the problem is, because of it being cast, they're fairly thick in construction and they also hold the heat. They don't dissipate heat as good as like a sheet metal tank, but they work out easier to fit because they're cast, they're moulded, so they definitely always fit. You know, like we do a rolled sheet metal tank, so it's radius bent here and here in all directions, for good airflow. It's welded inside and outside. Whereas if you have an intercooler tank like these, that are done in individual strips, they don't look as good. They've got square edges so they don't flow as well. And then if you have a big explosion, that's what happens. They split, too much boost, maybe a bit of nitrous, but usually a lot of boost in it, and they will split, you know. And that's one thing you don't want to have happen when you're out in the middle of nowhere.
So how do you keep hoses from blowing off?
We roll a lip on the end of the intercooler pipes or intercooler tanks that actually stops when the clamp's on it. It can't slide over that lip. So stopping a lot of people where they blow intercooler pipes off is because they don't have anything here to stop the clamp from sliding off. This is how we actually put that bead on the hose. We put a piece of tube in like so, wind it down, and then we just roll it around. We'll undo it, and then there we have this lip on the pipe to stop the hose from coming off. The clamp we use is this stainless steel clamp. It looks like a normal radiator hose clamp, but it's not. It's got a rolled edge on both sides, so when it's tightened up very tight on the silicone hose, it doesn't actually cut into the hose. Here we have a factory GDR Nissan intercooler. Comes out on all the GDRs, and a lot of people believe these are the ultimate street cars, but their intercoolers, because they're mass produced, aren't really that good in construction. A lot of people buy them and use them for putting on the other cars because they believe they are that good. These ones are very restrictive. If you look how small the cores are, they're very thin, so they don't flow enough air through them, you know. Whereas look at the size of the core here, so it's a lot more efficient. Getting back to what we said before about the cast tank and the fabricated tanks, is these ones will dissipate air, cold air better, whereas these ones, they hold the heat in. So making this a lot more efficient. By making this have colder air than it did before, he can up the boost to a good level, whereas he doesn't get detonation or anything like that.
Many people believe that simply upgrading an intercooler increases power. This is not quite true. An efficient intercooler will keep the intake air cooler, minimising loss of power on a hot day or when driven hard. But it's the opportunity to run higher boost now that the air is cooler that will actually increase power. But at what cost?
If you do a front mount intercooler kit or fitting on a 200SX or a WRX, usually the cost works out for the large size intercooler with all the polished tanks, polished piping, silicone hose, clamps. We chop the bar, we mount the blow-off valve, like drive-in, drive-out, usually goes around $2,400.
The next part of a complete turbo system is the blow-off valve. Hard to believe, but they weren't originally designed to be part of your sound system. Brett from GFB explained what it's for.
The blow-off valve is utilised on a turbocharged car basically to bypass excess turbo pressure when you shift gears or when you lift off the throttle suddenly. You get a build-up of pressure in the system, and a blow-off valve will release this by opening up the piston. A lot of factory valves have a very small flow capacity, as you can see by the small outlets and inlets, and the other difference is in the way they operate. The factory one will usually open with a vacuum signal alone, which means that any time your manifold is in vacuum, the valve is wide open and your turbo will be pumping the air around in circles. An aftermarket valve, most of them operate with a vacuum signal and a boost pressure signal. So you have the vacuum on the top there. When you close the throttle, you have vacuum here and you have positive boost on this side. So the vacuum neutralises the spring pressure and the turbo boost pushes the piston open. So this means that you will have the piston shut until you actually need it. This one's off a 95 WRX. It doesn't flow a whole lot, and the other thing is factory valves tend to leak.
Now, do you really need a turbo before you can fit a blow-off valve?
I get that question asked to me quite a lot, more than you'd think, but yes, you do need a turbo. Basically you need positive pressure in your manifold to utilise a blow-off valve.
So how do they actually make a sound?
Sound is pretty much a function of the back pressure of the blow-off valve, which you can adjust by changing the travel of the piston and also the area of the venting outlets. Basically, the smaller the outlets or the more turbulence the air has as it travels through the valve, the more noise it will make.
But doesn't loudness reduce the valve's efficiency?
Basically, yeah. If it's loud, then it means it's actually causing flow restriction. There's often a misconception that the spring tension is used for adjusting the boost level that the valve holds. Because of the design of the valve, when you have wide open throttle, you've got the same pressure on the top as you do on the bottom, which means that basically the valve will stay shut. When you close the throttle, you get the vacuum on this side, the positive pressure on that side, and that's when the piston opens up. So until you have that condition, the valve will stay shut, regardless of the spring pressure or regardless of the boost pressure you're running.
But if you want maximum blow-off valve efficiency without the noise, that's when a bypass is fitted to recirculate the vented air back into the inlet pipe. However, there is a way to have both.
What we call a hybrid valve. It features a recirculation port and a trumpet to atmosphere port. The advantage of this design is that it recirculates some of the air back to the inlet and some of it to the atmosphere. So you still get noise, but it's not going to upset a car with an airflow meter.
What if your valve's not working properly?
First of all, it needs to flow enough air to prevent compressor surge. Compressor surge is the situation where the valve doesn't flow enough air and the compressed air will force its way back out through the compressor, and you will hear this as a fluttering kind of a noise. And if it is doing that, then basically you need a bigger valve or the spring pressure is not set correctly.
After the blow-off valve, you'll often find a pop-off valve. These exist mainly to prevent overboost. It triggers when the boost pressure entering the engine reaches a preset maximum. The pop-off valve simply vents the excess pressure out of the system. And the final boost control device on all turbo cars is the wastegate, which simply wastes off exhaust gases to prevent the turbine wheel from overspeeding. Notice how the airflow into the turbine wheel is now reduced. There's two types of wastegates.
You have your integral wastegate, which is similar to this unit here. This unit here, where it's attached to the turbocharger and controls a wastegate flap valve on the turbine housing. Typically you would use a integrally wastegated turbocharger up to about 450 horsepower. Above 450 horsepower you need to look at running an external gate where you can A, control boost better, and B, get exhaust gas away from the turbine quicker. Runs on the same principle as an integral wastegate, but is just much larger in its capacity and its ability to get rid of exhaust gas. We have a valve similar to the valve that's used in an integral wastegate on an exhaust housing. That valve will actually lift off its seat and let gas escape from this port here into the exhaust system. Once you've reached full boost, the wastegate will continually open.
In the next video, we'll explain superchargers, how they differ from turbos, and the pros and cons of each.